Hi everyone, this is Martin from the University of Michigan. Today I'm happy to share our work on babysitting a language model from scratch with interactive language learning by trials and demonstrations. There has been significant research into the role of feedback in interactive language learning. For example, communicative feedback involves the explicit negotiation of shared understanding with a communication partner in order to achieve and maintain a common ground. On the other hand, corrective feedback includes responses from caregivers that provide corrections for potential mistakes in children's utterances, including variants such as negative evidence, reformulations, or recasts. Corrective feedback is known to be helpful in second language acquisition, but researchers largely dispute its availability and effectiveness in human first language acquisition. In the context of AI models, corrective feedback can be massively available, and its effectiveness should be reconsidered. Our research question is, does corrective feedback benefit neural language learning, especially word acquisition? And what are some phenomena under such a training paradigm? Recently, a lot of efforts have been made to connect neural language models to language acquisition studies. For example, several efforts have explored potential mechanisms that contribute to the efficient language learning in vision language models by incorporating non-linguistic input such as multimodal stimuli and/or communicative feedback. Neural language models can be useful to language acquisition despite not being designed as cognitive models. As proof-of-concept models, they're independent learners of humans and show what is possible in practice for models and in principle for humans. As hypothesis generators, they can propose new hypotheses about language learning in children, making testable predictions. The benefit using neural language models include that we can easily conduct ablation studies without ethical consideration and the easy access to model weights over time, allowing for large-scale probing. Modeling corrective feedback in computational model presents challenges because it is impractical to recruit human subjects for this purpose. We thereby introduce our trial and demonstration framework. The student model begins with a production-based learning, creating an initial utterance. Then, the teacher model steps in, generating its version of the text as a demonstration. To ensure the student model recognizes the teacher's response as better and learns effectively, we use a reward function to evaluate these language outputs. We start by training a typical generative language model. At different training steps, we can prompt the model to generate sequences of text, therefore obtain a huge dataset of text-step pairs. Using this, we can develop a neural age predictor that predicts the expected training step of a language model given a model-generated text. We propose using the model's age as a natural neural reward mechanism. Here's how it works. If a model at 1K step produces a sentence typical of a model at 10K step, it should receive a positive feedback. Conversely, if a model at 1K step produces a sentence that is typical for a model at 100 step, it should receive a negative feedback. This approach helps to align the learning process of a language model with the expected developmental milestones. Together with the teacher model's demonstration, we adopt reinforcement learning to the student language model so that it can learn interactively. And also, following previous work, we alternated between the interactive learning paradigm and the non-interactive learning, aka the causal language modeling, to simulate how humans could learn actively and also passively by overhearing others' talks and languages. To evaluate how well the model learns a word, we adopt the surprisal metric, which is negative log probability of a word aggregated over 100 contexts. We fit the learning curve using a double sigmoid curve, where the plateau of the curve corresponds to the unigram appraisal. To measure how fast the model learns a word, we adopt the age of acquisition metric. In children word acquisition studies, AOA is when 50% of the children can produce a word. Similarly, previous work determined a cutoff to be 50% between the baseline appraisal and the minimum appraisal. We further evaluate the cutoffs over 50% to 95% with a step size of 5% for robustness. In our experiment, we repeat the experiment on 2 different corpora and test it on 2 different vocabulary sets, each with 5 different random seeds. We train a GPT-2 model as the teacher model and use a randomly initialized GPT-2 model as the student. To make sure the reward model fits the curve, we fine-tune a Llama 2 model for this role. Our main finding is that the TND leads to faster acquisition of words, although eventually the final performance converges to the teacher model. Further, through ablation studies, we show that both the trial and demonstration are important in this group. We observed that TND leads to earlier neural age of acquisition, especially in the earlier training stages. Also, students under the TND framework quickly pick up a large volume of effective vocabulary, but of course, eventually, their vocabulary capability converges to the causal language model baseline, as expected. We now keep all experimental setup untouched, but experiment with smaller student models. We see that each TND model still outperforms the COM baseline of the same size, and even surpasses the COM baseline of larger capacity, especially in the early steps. We further study the role of teachers' word preferences in student language learning by masking out a subset of words from teacher decoding. Our findings indicate that the absence of word from teacher's demonstration leads to slower learning speed for the student models. We finally show a practice makes perfect effect on students. Especially, we observe that the attempts of trials are highly correlated to the acquisition of functional words and predicates, whose semantic depend on the other words. This effect is, however, not observed in groundable concrete nouns, whose semantic depend on the groundable objects in the visual perception. We present the beta weights between their mean appraisal and the cumulative word frequency throughout training for predictor analysis. The results once again confirm this observation, where the more the student try, the better they learn the function words and predicates. Of course, there are several limitations of this work. For example, in the future, we plan to study an iterative setting where the teacher and student can continuously improve. And also, we plan to study less accurate and imperfect real-world models. Future work should also study other forms of reward, especially in intrinsic forms. And we also plan to explore more in terms of the tokenizer and other languages. Thank you for listening.